Hi, I'm Ariel Bieler. Welcome to my session, Best Practices in Handling Machine Learning Pipelines on DGX Clusters. You can find me online at LSTMeow. And let's begin. DGX, what an incredible beast. Even a single compute node with so many A100s is the real deal. A supercomputer in a box. The difference is that you don't need a supercomputing center to host it. For me, this is a mind-blowing fact. Every time I think about it, it means that you're technically able to provide leadership class compute on premises to your research teams, of course. If you are a researcher or a team leader, think back. Think back and count the number of times you could not pursue promising directions because of hardware constraints. With so much compute, the question is now one of scheduling, not of feasibility. Of course, when considering the entire organization's research goal, the scheduling transforms again to a feasibility question of a different breed, more related to policy, because machine and deep learning research will always be hungry for more resources. How do we navigate between the needs of all researchers with a relatively constant amount of compute? And you know what? Is this close to policy? Can something be done in the trenches? Are there magic solutions that can ensure everyone is 100% productive and the cluster is running at peak usage? You just know that there is no miracle cure for this, but there is a methodology that helps. And this is the topic of the next 35 or so minutes. Let us start with the obvious. So you got a DGX cluster. The main thing you need to do is to make sure utilization is optimal. Problem number one is heterogeneity. No two research projects are the same, and the pace is anything but constant. Most notably, there are periods when a researcher needs to iterate endlessly until there is a breakthrough. Then, she will want to scale up and use whatever resource can be spared for her. This both introduces seasonality in usage patterns and inefficiencies, since scaling is not entirely linear. Now, put it in the context of several researchers working together. That's problem number two. We don't just need to make sure that each research is conducted efficiently, we need to make sure that there is no traffic jam. In other words, when the researchers need the hardware, they can reach it. And naturally, we should not interfere with the workloads on the cluster, nor the opposite, leaving idle GPUs empty just in case. And actually, this slide isn't just for machine learning research on a multi-million-dollar cluster. It fits all computational sciences on any shared hardware. So what is unique about data science? Well, in data science, the research iterations may vary greatly from one another and sometimes occur much faster than other research. We are still in the stone age of applied machine and deep learning in data science, and the only thing that works is to do the following. You consider the task on a whiteboard, actually the electronic equivalent, that's a Jupyter notebook. If it looks like you have something that can work, you build a prototype. You make sure it's not a dud, and then you start scaling up in order to tackle real-world data. At this stage, you handshake with the business logic layer in your organization, which might help to clarify or even reconsider KPIs and approaches. Then you go back, maybe back to square one, maybe just back to the prototype. This is a convoluted and discontinuous process. My passion as an evangelist is making these gaps disappear and helping researchers seamlessly move from each stage, reducing code and environment changes. I call it doing R&D, not switching between R or D. In soundbite form, it means scaling up or down without code changes. This approach at times clashes with having all of your compute managed at a cluster. So just solving the previous slide isn't enough. You would need to do it while facilitating the researcher's daily work. And this wasn't easy until very recently. Now, I will speak very broadly about the suggestion. Then I will give a hand-wavy theory, some best practices and that implement this theory, and an actual example using them. The solution is the blanket is too short. Okay? There is no magic solution. It's a way to deal with the situation. You start by relinquishing control over the blanket. Research is chaos. You know better than to try and micromanage it. So the resources needed for rapid iterations should not be managed by anyone else than the researcher. This can only work if there is a complete transparency in research availability. You need to know without asking anyone else if a GPU is free now. And then you move to step 2, measure efficiency. But that does not mean that you cannot provide feedback and educate the user regarding her usage patterns and ROIs. These can be simple metrics of how much compute was used for each project, or can be broken down into stages of work. Next, you reevaluate balance. Using metrics from all the researchers, you can periodically adjust the usage restrictions either individually or as a group. Adjustments shouldn't just happen at the end of a sprint. For example, you may assign resources to more than one individual or task, prioritizing primary and secondary users. Lastly, you reevaluate provisions. Also, projects change in organizational importance. Resource allowance should reflect actual project value. Now, these are not just a set of arbitrary rules I dreamt up. It's a condensed form of what I call lessons learned during a decade of supercomputing. Okay, now that we all have supercomputers, these same methods are relevant to all of us. But can we apply these in a data science context without a hefty bureaucracy penalty? Well, first, I want you to identify where you're at in this situation. Relinquishing control and managing is for team members and the team leader. The directors have to do the reevaluation of provisions, but the point here is that the DevOps is at the center, but has no actual decision-making capabilities. The DevOps needs to facilitate everything, and it actually makes the DevOps work easier. And I'll show you a little bit later. Now, let's do the theory of how this actually works in practice. Okay, you do it manually. I'm not saying you can't automate it, but you just need your precious R&D to debug the actual models, not the provisioning of resources. So assume now that repartitioning and provisioning of all the resources is easy. I'll show you later that it is. And now let's talk about the general map of what should be done. Okay, and it's a crude overgeneralization, and I love these because they are useful. But you have three types of workloads on a cluster. You have the short jobs. These are low-powered, relatively quick experiments, exploratory data analysis, pre-processing, quality checks, model fine-tuning, transfer learning. And then you get edge cases. These are massive experiments that, okay, think of the equivalent of training GPT-3 with your respective capabilities. So something that runs for a long time and uses up a large chunk. In the middle, we have the default kind of workloads. It might be stable pipelines for training, auto annotations, hyperparameter optimizations. I'm not saying that there is not just one type of job, but everything that's graduated from short and became automated can be lumped up to here. And now the exciting part. Between the data center and the workstation, a researcher will always prefer workstation because the experimentation is interactive. This has always been a psychological barrier. Why should a researcher wait to do a quick experiment? And it often might fail, and then you have to wait to start again. Even a delay of several minutes can be frustrating if you do it time and time again. It requires some adjustments. Only the prospect of time to results can move the researcher to migrate to the cluster. Okay? Meaning, I have something that works. I want to now go and run it on a big machine. Now there's a concept of transitioning. I mean, it's extra debugging and additional waiting. So before I make my suggestion, I want you to note that the edge case here, this heavy, isn't always available in organizational settings because it needs a lot of coordinations. And this is my suggestion. It's an ideal, okay? That the data scientists will have a pool available for them to grab for all the short jobs that they need with zero wait time, maybe time for making a coffee or something. We would want the same for the regular size workloads, but if we use them only for stuff that's measured to be efficient and scales well and maybe controlled by machine learning engineer types. Lastly, we want to have the ability to cordon off large chunks of the cluster to do some heavy weightlifting, and that should be controlled by the DevOps. So my theory is that it's already a possibility with DGX and an open source solution called ClearML. It enables this picture here. Light now, medium soon, and heavy later. Again, not automatically. I told you there's no magic, but if you iterate on your provisioning, as I suggest, you can reach a situation that is similar to this. Okay, so I mentioned ClearML. I need to explain what it is because I need its unique capabilities for the following. So ClearML is an open source 3-part MLOPS solution, an SDK, a management server, and a smart agent, which provides all the things here in the list with super easy integration. And these are the things that we should care about in an R&D setting. Most importantly, the whole thing is DGX ready, and it enables orchestration and provisioning in the manner that I need. Specifically, setting up no-hassle interactive sessions on the DGX, meaning that we merge these two. I will show this in a minute. For more details about our product, please visit clear.ml. Now, concrete best practices, so what I described will make some sense. I call them the ABCs of computing, always be computing. It means computing on tap, minimum waiting, easy to operate. Remember, we need to scale up and down without code changes, and we need actual data scientists to be using this. And also easy to configure because we want to be constantly changing around provisioning. Okay. So in order to get compute on tap, I would be using a unique capability for A100s called MIG, together with something that we developed called ClearML Session. Okay, so what's the smallest chunk you can use in order to run your workloads? On an A100, it's actually 5 different answers. MIG technology provides hardware slice that can be used as an individual GPU. So if you have 8 GPUs on a DGX, you can, for example, have 56 mini A100s, which are approximately like T4. So it's still good for most of short workloads. And if you need more memory, you can reconfigure each GPU in many ways. If you have provisions for a project, for example, 4 GPUs to use by 3 teammates, you can, for example, use 3 GPUs as full-sized A100s and slice the 4th into 7 small pieces, meaning that each team member can probably run and effectively 2 or 3 concurrent workloads for short loads. And then you have them sharing the big 3 for the large and the medium workloads. So also a comment, there's no GPU to GPU communication at MIG mode, and also other stuff doesn't work, but for all practice and purposes, it's what you need. Now I'm going to show you how it is to get an interactive session on a MIG slice. The demo is for Jupyter, but VS Code and even Direct SSH work as well. Okay, so now I'm going to use ClearML Session to spawn a Jupyter Lab session on my DGX. All the DevOps has been taken care of in this demo. It wasn't really hard work. I just need to know the username. No need to configure where the machine is. Just need to know that I have a queue, which has a DGX MIG instance connected to it. I'm deciding on the Docker that I want installed there and specifying the packages that I want. This is the basic use case of ClearML Session. There are more use cases for that. It's a pretty neat tool. Basically, it has keep alive that makes sure the connection is always on. All the network is transport is automatically encrypted. And we can also do collaborations. I can share the session with someone else that has access. But never mind that. Let's execute this. Okay. Now it's actually verifying credentials. Yes, this is all the settings. You can cache those, and I'm launching the interactive sessions. I might need to pause here because sometimes it takes a little while, about 20 seconds or so. Let's see. Basically, there are 2 main use cases for this, but for our purposes, we just need to get a GPU now to work and get a Jupyter notebook on it. Okay? Okay, now it's queued. And I'm going to pause here. Okay, didn't need to pause a lot. And now I'm just waiting for the waiting environment setup to complete. Okay, so now I need to enter the password because the access is a little bit more tight, but that's okay. So this is what you get. You get a link, and you have, when you press this link, you get, lo and behold, a Jupyter server on your DGX. Let's check it out. And voila, we got A100, but look at this, we have a MIG device on it, and that's us, a single MIG device. This is the amount of memory. Just make sure that the GPU works. And that's it, actually. You are now able to use whatever resources that you need. And look at the response time, right? And it's really far away from me. I'm really proud of this. And just know that there's also VS Code. And let's go on with the presentation. Okay, now that we saw that it's awesome and it works, let's discuss practicality. As I mentioned, you have a mix of MIG and regular A100s together, and you need to act accordingly. With the MIGs, you need to vary the MIG slices. Don't just do one size fits all. You need to constantly think about, destroying partitions and creating something that fits better today or tomorrow, and not just slicing it once and forgetting about it. It really depends on the time that short training takes. Also, don't forget you can assign multiple roles per slice. For example, if you have a small slice that does data processing almost never using the GPU, you can also use a slice the same slice for visualization jobs, and so on and so forth. Okay. Now, regarding the fixed GPUs, you need to provision them. You need to make sure that you are using them like you should. Maybe assigning a single GPU for a workload, or maybe multi GPUs for a workload. Maybe a full rack for a workload means 0 MIG slices. And if you want a multi-rack workload, so that's the edge cases I was talking about, of cordoning off large chunks of the cluster. Because face it, a single DGX rack is a lot. Okay, so let's talk about easy to operate. As I discussed, we want to seamlessly move between light and medium with no code changes. That means that you develop on short and then flick a switch and go to do heavy weightlifting. How do you do that? Well, how is it done without ClearML? How do you do it? You have a DGX. How do you do it? Well, you do it manually because it gets the job done. You SSH to the machine, you start a Jupyter session, you connect to a Jupyter server, you load your notebook, you run all cells, and then you forget to tell anyone that you're done. Also, a prerequisite for this will be to email everyone, making sure that nobody needs a GPU. This is something that works, but it's not as convenient. Think about the following. What if you could add 2 lines to your Jupyter notebook, and it will turn it into a job template? It will save the Jupyter notebook as an artifact within it, but it can be executed as a workload via a web UI. Okay? This is just these 2 lines that you can add. Now you want to control it from the web UI without changing the code and without needing to go back into the Jupyter notebook. Well, for that you have what we call Task Connect. You create a dictionary, you can create a class, a data class. It works with a lot of stuff. And you use it in your task accordingly as a dictionary, but since you connected it, you can override these things from the UI. Think of it like argparse that actually works for everything, including Jupyter notebooks. So with this, you can take a template and launch it, and I will show it. But first, let me restate what it means. You, instead of using the Jupyter on the machine, you use it on an interactive session, make sure everything works. Then what you've done is translated into a template which you can clone, modify via the UI, and then queue it, which means that all the resource handling is done behind the scenes for you. Okay, so now we have a DGX machine. We have 8 GPUs. One of them is subdivided to MIGs. And I want to actually run a workload, let's say on one of these GPUs and another workload on 2 of these GPUs. Okay, great. So we have here the workers that I have ran. I'll show you later how to set this up, but we have 2 workers on a MIG instances, 1 worker on a single GPU, and 1 worker on 2 GPUs. Okay, and we have queues for them. 2 100, 100, and 2 MIGs. And for the workload, I'm going to use NVIDIA TLT, the Transfer Learning Toolkit. It's fully integrated with ClearML, and we got version 3 coming very soon. But for this demo, this will suffice. It's using the TLT Docker container. And we're going to run this. But first, I'm going to pause and show you this. This is exactly the task connect I've shown you before. I can now access, for example, I want to change one of these specs. Maybe I want to change from ResNet 18 to something else. Or maybe I want to change one of the TensorFlow flags inside. I can do that by double-clicking. Maybe I want to change the name of the log, for example. I can double-click and say, change it here. And this will change the options inside the code with no extra commits and no code changes. And now I want to commit this and queue this. And let's say on a single GPU. And also, let's clone this. Okay, let's say I want to see how efficient it is to work on 2 GPUs. And I'm going to enqueue this on the 2 GPU queue. And that's it. You can see already in the first one, it's already unpacking and installing the packages inside the container. And we are basically done. So this is a very quick demo of the powerful features of orchestration that you can have. Finally, we have to make sure that it's easy to configure, meaning that whatever I said about doing the reprovisioning and changing everything can be done by several people, and the DevOps only is needed for changing partitions, for example. Okay, so now we're going to take a DGX machine with 8 GPUs, split it to MIGs, and set up workers on some MIGs, A100 machine, and 2 A100 GPUs. And in order to do that, we first need to get on ClearML and configure our credentials, either in a ClearML server that you set up on your own or the ClearML free SaaS. But this assumes that you have already the clearml.conf file, because you would need it to contact the server with the workers. First of all, we install the worker, ClearML agent, and then we need to set it up. Okay, so what I'm going to do now is to start a ClearML agent daemon using this config file that I just shown you. It's going to use the queue A100 that I've already created in my ClearML server. Use GPU number 1, so it's the second GPU. I want to put it on Docker mode, and I want it to run it detached. Okay, and that's all. Okay. Now I have a worker, single worker. Let's check it. Okay, here is my worker. This is my worker, and I like it. Now, let's go back. Okay, And now let's do a worker that is on 2 GPUs. So something like this. Okay? That's it. We can go and check it as well, but we'll check it later. Now the important thing is MIGs. Okay, we see that we have these 7 GPUs, and remember, these are already hooked on workers. Let's split GPU 0. First of all, we'll query and see that MIG is enabled, right? And now we want to create a compute group, but only on this first GPU. Okay. What is my password? Again, this can be done in a non-quick and dirty role-based access, but I'm doing it right now because this is how you would do it initially. See, now I have 3 MIG devices here. Let's do something, I don't know, differently. 1, 2, 3, 4, 5, 6 on the 7th GPU, which is also MIG enabled, the 8th GPU, sorry. Okay, so now I have these on GPU 0 and these on GPU 7. And now all I need to do is set up workers for them. And for this, I will pause the video. Okay, now I'm going to use this denotation 7.0 to set up. I have a queue called MIG small for, or actually this is not a small, so I will use not the first one. Okay, this one. Okay, and also another one, and also another one. Again, all of this can be automated. I'm just showing you for how it will look like. And now we'll go to the app and watch my resources. Voila. Right? These are the ones. And we can look at the queues. So this one has all of these workers on it. And we are good to go. We can do the ClearML session that I showed you before. Okay, I hope this was understandable. And let's continue. To summarize, what I've shown you is not a blanket solution. It's a combination of hardware and open source infrastructure and software called ClearML to help you use your software and hardware together in a way that is frictionless, especially when doing scale-up. Evidently, you also get good MLOPS building blocks that might convince you to look at us further. So what I'm going to do now is I'm going to answer any of the Q&A questions that you've sent me in the chat. And there's time for more questions. And I'm not sure, I think you won't be able to see each other's questions. So I'm going to answer some of the frequently asked questions right now. First of all, if you want to learn more. So we have 2 other sessions on in GTC. We have a session that's entirely on pipelines. It's the first one here. And we have another one for how to do MLOPS with teamwork, the thing that I described very, very briefly with adding the 2 lines and enqueuing the task. And also you can see for yourself, ClearML free is free, actually for teams. You add 2 lines to your notebook after you register, you install the agents like I've shown you, and you start working. So it's, a matter of minutes until you test it. Other questions that might appear. First of all, how is it compared to X? Okay, so first of all, X, mostly people look at stuff like MLflow, weights and biases. What else can I think of? DVC. It's important to note that this talk is specifically about an orchestration situation that I think this one has the best and unique solution to cover all of the bases with the least amount of code that you add to your own system. There are many ways to compare the product, especially in this very convoluted MLOPS world. I urge you, if you have any difficulties in comparing products, just hit me up online, LSTMeow again, and I can give you the rundown. Also, I can refer you to maybe other people that can give you comparisons who are not vendor representatives. Now, another question that people ask, yes, ClearML is open source, free. You can install it on premises and you get everything that I've shown you here without any dependencies outside. It really is compliant with many security protocols, and it's really actually it's used by more than 1,000 organizations. So I think it's really safe to assume that if it works for you on a test case basis, it will scale with you to whatever heights your research needs. Also, there's some stuff about deployment and production, which I've kept outside of this discussion. Now I'm going to add just silence, so I can answer all the other questions that you might have asked. And just again, any questions that you failed to get an answer from me right now, look me up on LinkedIn, Twitter, Reddit, Facebook. I'm LSTMeow everywhere. Really happy that you listened to us today. Thank you very much, and enjoy your GTC experience.